Last video, if you remember, we talked about electric potential due to a dipole. Today we are going to take a situation when you have group of charges. So when you have group of point charges, then what's going to be the net electric potential? So the situation is electric potential when you have group of point charges. So it's quite simple. Simple means at this stage we know something which is known as superposition, right? So due to each point charge, what's going to be the potential? We are just going to add. So if you add those potentials because of the discrete charges, it comes out to be, the algebraic sum comes out to be the net potential. So if you want to write it, the net potential is a generalized equation. So it is just the summation. Suppose you have charges n, y is equal to 1 to n charges, and you have for individual potential because of first charge, potential because of second charge, just need to add it algebraically. And we know because of point charge, this equation could be written as 1 over 4 pi epsilon naught is the constant term we take out of the summation, and we'll just be adding up this Qi and Ri. That Qi appears in the numerator, Ri appears in the denominator, and this could be a generalized equation. So net potential is 1 over 4 pi epsilon naught summation, मतलब अलग-अलग add करेंगे Qi Ri. So we'll take an example. Let's take an example. Suppose we have charges, one charge, second charge, third charge, and fourth charge. Okay, and these are arranged in a form of square. And suppose the distance between the charges is dq, that is the four corners of a square. So all of those distances that's there is d, and suppose this is q1, this is q2, and this is q3, and this is q4. And we want to find what is the net field here, net potential here at the center, which is P. We are interested to find what is the net potential at P. What should be the approach? And we'll give the values. Suppose Q1 we take as positive 12 nanocoulomb. We take Q2 to be, suppose, minus 24 nanocoulomb. And suppose we take Q3 to be positive 31 nanocoulomb. And suppose Q4 we take to be positive 17 nanocoulomb. And we are interested to find what is the potential here. And we also take, suppose, D to be 1.3 meters. So with these given things, how can we apply the superposition principle? So we'll write it here. The net potential at P is going to be equal to 1 over 4 pi epsilon naught. And we'll put in the bracket Q1 and R1 correspondingly. So we'll take this distance to be r, suppose. So what's going to be the r? We can, from the geometry we know that if you join this is d, this is also d. So from geometry, this distance from here to here will be equal to 2d square under root. So from Pythagoras we can find this is square plus this is square is equal to this is square. So this is equal to under root. So this d square plus d square is 2d square, and the square of this diagonal is going to be 2d square. So length of this is going to be under root. So this comes out to be under root 2d square. So from here we can find the relation, right? So this R is right at the center. So therefore R is going to be 2D by 2, right? So if you multiply both sides, numerator and denominator, by root 2, we'll get this to be 2 over 2 root 2 D. So therefore R comes out to be D by root 2. So we'll be using this R there in the equation. So if you apply the superposition principle, it will be Q1 by R plus Q2 by R plus Q3 by R, and last one is Q4 by R. So we take R common, so therefore this VP is going to be equal to 1 over 4 pi epsilon naught 1 by R, and Q1 is given plus 12, so let this be 12. Q2 is minus 24, so it will be minus 24. Q3 is plus 31, so it will be plus 31, plus 17, it will be 17 nanocoulomb. So the unit is nanocoulomb. Well, so therefore we get potential at P comes out to be, now 1 by 4 pi epsilon naught, we already know it is 9 times 10 raised to the power 9 Newton meter square divided by Coulomb square. Okay, now if you add up, let's take the help of calculator, it comes out to be 31 plus 17 okay minus 24 comes out to be 36. So this comes out to be 36, right? Nanocoulomb means 10 raised to the power minus 9. It will be in coulombs now. So, and then in the denominator we'll have R as well. Now R is given D by 2 and D is 1.3. So this is 1.3 divided by root 2. So I'll make it 1.3 divided by root 2. Approximately it comes out to be, say, 0.9. So this comes out to be approx 0.9. So 1 meter would get cancelled, coulomb gets cancelled. So this comes out to be in joule per coulomb, which is volt. So if you calculate this, 10 raised to the power minus 9, and here 10 raised to the power 9 gets cancelled, and 36 times 9 comes out to be 324. So this comes out to be, if you calculate approximately, it comes out to be 324. Let's see, 324 divided by 0.9. This comes out to be approximately 360 volts. So the answer is 360 volts if you calculate, and that is how we just apply the superposition principle. So it's as simple as that. With this discrete charges, we use the same process, but when you have a continuous process, when you have a continuous charge distribution, then we are going to use calculus to calculate the net potential. So in the next lecture, we are going to take up an example wherein we have a rod or we have a disc, and then we want to find a potential. So watch the next video for the same. Thank you.